Hi, in this video, I'll be going through compact spaces of Rn. So, in the previous video, we went through what is compactness, and I'll recall it by saying that for every open covering of X, there exists a finite subcovering of X. So it's quite a nice slogan, but you really have to remember the definition and practice a lot to familiarize yourself with doing the questions. And so now it says that we want to prove big theorems about compactness in a sense that we want to know when and what subspaces are compact. And really, in the Euclidean spaces Rn, you're compact if and only if you're closed and bounded. And really, it is saying we will first start to prove that later on, but we will need this corollary first, that every closed interval is compact. And this is the Heine-Borel theorem in R1. And so, suppose that we now want to prove this, that every closed interval is compact. So suppose that your interval is not compact. And so that means there exists an open covering of this interval which does not reduce to a finite subcovering. And so now you can split the subset into two equal parts, so that A to A plus B over 2 and from A plus B over 2 to B. Well, one of these intervals cannot reduce to a finite subcovering, because if both did, then then the whole space can be reduced to a finite subcovering and is compact. But now we find, using this open covering that does not reduce to a finite subcovering, neither of this can reduce. And so if you define your I1 to be I naught L, if I naught L does not reduce to a finite subcovering and equals to I naught R otherwise. And we just continue this process, and so we can define IN to equals to AN, AN plus BN over 2 if ANL cannot be reduced to a finite subcovering. And it will be defined as INR if it can be. So this is n plus 1. So this means that now AN can only increase from here on out, because it either becomes the A plus B over 2 or it stays with itself. So it's monotonically increasing and is bounded above clearly by B. And Bn is monotonically decreasing and bounded below by A naught. So A is A naught. And then we know the difference between the two will just be B minus A over 2 to the power n. And so by the least upper bound property, this sequence will converge and this sequence will converge. And by the third property, it says that they will converge to the same limit. And so the idea now is we let P be the limit, and since I naught is closed, P will be inside this interval, which means, and this interval is a subset of the open covering. And so that means there exists one of the covers such that P is the element of that cover. And because P is the element of this cover, then this cover is open, you can find an open neighborhood such that is contained within U alpha naught. And this interval, this open neighborhood of P, must contain the sequences AN and BN for large enough n. And as a result, it means that the interval from AN to BN now is contained within this open neighborhood. And this open neighborhood is contained in the one piece. And so it means that in the end, IN is covered by a single piece, which is a finite subcovering. But that's a contradiction, because when you define it, it means that IN is unable to be reduced to any finite subcovering. And hence, this contradiction shows that our initial assumption is wrong, and so every closed interval in R is compact. And because of that, we will now prove the Heine-Borel's theorem in Rn, where it says that a subspace is compact in Rn if and only if it's closed and bounded. And it follows because if it's compact, then because Rn is Hausdorff, you know it's closed. And because Rn is also a metric space, you can easily, because it can be reduced to a finite covering, so like you can just imagine you have the finitely many number of balls now that covers K. So you just take the ball with the largest radius and that will be the bound, and so you're done. Now conversely, suppose that K is closed and bounded. We already shown that closed sets are compact, so K will be a subset of this. There will be a bound for K, so because K is bounded, you can find it to be K will be a subset of this N cell. And because this is an closed interval, this is compact, and we already shown that finite products of compact spaces are compact, so this whole thing is compact. And so it's closed subspace of a compact space, and so it must be compact. And hence, we are done. And this is a really important theorem in knowing when a space is compact in Euclidean space, and that is when it's closed and bounded. An example is the unit sphere and the unit closed ball. Because it's closed and bounded for both of these, then they are compact. And so, why do we care so much about the Heine-Borel theorem? Well, it really helps us prove the extreme value theorem in a more, I would say, more natural setting, because now you're talking about topological spaces. And so since X is compact and F is continuous, the image will also be a compact subspace of R. And because you know it's a compact subspace of R, by a Heine-Borel theorem, Fx is closed and bounded. And so, because Fx is non-empty, since it takes elements in X, by the least upper bound property, and since it's bounded, you know that the supremum and infimum exist. And because they are closed, this supremum and infimum will lie in the image. And this actually proves that Fx will attain the maximum and minimum value, because the sup will be the max and the inf will be the mean. And because both of them in the image, that means there exists an X such that Fx equals to the sup. Likewise for the inf. And now really compactness is essential because it creates the image to be closed and bounded. And so this is a much simpler proof and a more intuitive understanding of the extreme value theorem in a general setting like this. And so I've come to the end of this video. This is a short video to really get us started off with understanding compactness, and I hope that it's clear now when we use the compact definition and how it helps us improving theorems. Hope you have enjoyed this video. See you again. Bye.